Good evening. My name is Taylor McBride, and in completion of the requirements for Groundwater Hydrology CVEG 5243 at the University of Arkansas, I submit my studies on superposition and image well theory. So to do an overview of what we're going to do today, we're going to go over the hydrological mechanics, basically what's happening underground, how that water's moving. Then we're going to go into Darcy's Law, a very important part of groundwater hydrology as a whole. We're going to discuss the different types of aquifers. There's a confined and an unconfined, and we'll go into depth in that very shortly. We're going to go over superposition. We will go over image well theory and discuss what separates the different types of image wells and as far as the boundaries go. And then we will go over the accuracy of this method, and I will give you my conclusion. Starting off with Darcy's Law. So Henry Darcy, 1803 to 1858. So he was kind of the father of the groundwater hydrology studies. He basically started off with fluid mechanics and then moved into fluids through like a porous medium, such as sand. And so if we skip to the bottom here, we have Darcy's Law. Q is equal to Ka times the quantity Pb minus Pa all over mu L. Those P's are pressure. So what happened was we switched, we didn't switch, we added Darcy's Law to the equations of conservation of mass, and we came up with this guy here. And that's a very user-friendly version of Darcy's Law. We have Q equals negative times DH over DL, which your negative K there is your hydraulic conductivity. That's basically, we'll go over that a little bit more in a second, but that's, every type of soil, every type of medium has their own given hydraulic conductivity that can be measured. Okay, and A is the surface area, and then we're going to do the partial of H over the partial of L, which is basically just like a gradient. So the negative sign is there because fluid flows from high to low, it actually goes down. We think in general of things increasing going up, so the negative sign is there as it, it starts at high elevation, goes to low elevation, and that's going to be positive for us. Same thing with pressure. Okay, so we have two different types of aquifers here. We have a confined and an unconfined, and we're basically about to go over the in-depth difference in that. So basically, what it comes down to is there a confining layer above the aquifer? So with a confined aquifer, we use the transitive equilibrium equation, which is the second partial of H over the partial of X squared, and that's equal to the storativity over the transmissivity times the quantity of the partial dH over dt. Now the storativity, as you can see, it is the volume of water released from storage per unit decline in hydraulic head. So it's just basically how much water that's stored up in the voids of the soil or rock or whatever you have, how it is released per unit decline in the hydraulic head over here. This is the hydraulic head coming down over there. Okay, the transmissivity, that is the the water flow rate through the medium. That's a big thing that Darcy started off in, water through the sand columns. And moving on, we have Darcy's equation for the confined aquifers, and that's the 2 pi times Kb, which we've said before, the K is the hydraulic conductivity, it's just a measurement of permeability, times B, which B over here, that's the height of your aquifer. The distance from the bottom permeable layer to the upper permeable layer, which the water flows through. Actually, I believe I have it flowing through this way, but that really does not matter too much, or at all. Okay, then we have the hydraulic conductivity, which we spoke about earlier. Now, the thing about the confined aquifers, like I said before, it has the upper and the lower confining layers. Both of them are impermeable. When you have water flowing through something like that and it's confined, there's going to be a pressure associated with it. And so, takeaway from this is when you poke a hole in a pressurized system, such as putting a well down into a confined aquifer, you're going to have a jump in the piezometric head. When the water's coming through, if a release of pressure is going to cause that to jump a little bit higher. Some old fluid mechanics stuff there. Okay, moving on to unconfined aquifers. So the governing equation for unconfined aquifers is the second partial of h squared over 2 times the partial of x squared. Now that's equal to the SY, the specific yield, over K, the hydraulic conductivity, times the partial H over partial T. Now the specific yield, this is a little bit tongue twisting here to describe. The specific yield is the volume of water released from storage per unit surface area of the aquifer per unit decline of the water table. Okay, so we have the water table coming down, we have the water being released out of the voids, and then we have the surface area, of the aquifer itself. Okay, so like we said before, the confined aquifers have a confining top layer. The unconfined aquifers do not have that. They rest on the bottom impermeable layer, no confinement on top. They get their supply of water through, whether it be rain or all types of water that's coming through the soil from anywhere, and that's it comes through and stores in this aquifer. That's how these aquifers are formed, how they keep their supply, and the how the confined aquifer had a top and a bottom causing pressure through that. The unconfined doesn't have that top pressure, so basically the top of the piezometric surface, that's going to be at atmospheric pressure equal to 1 atm, equal to 101.325 kilopascals, equal to 14.7 pounds per square inch. Just kind of depends on if you're working with metric or what you're working with there. And moving on to superposition. Okay, the superposition principle, states that for all linear systems, the net response at a given place and time caused by 2 or more stimuli is the sum of the responses which would have been caused by each stimulus individually. So basically, we have something coming on, a response, and we have 2 different things acting upon it. We have something we're trying to figure out, and we have 2 different forces or whatnot acting on it. This is not something that is only associated with groundwater hydrology. It's been seen and very much used in electrical engineering. I actually got to use that when I was taking my intro to circuits class. In physics, current change, magnetic fields, you can use superposition to solve all those problems. Mechanical and structural engineering, they overlap a little bit, and I believe that was the first time I ever dealt with superposition was in structural analysis, when you have combined loads on one beam and you're trying to discover the beam deflection in there. And then of course hydrology, hydrogeology, and that's what we're doing today. We're finding drawdown. Okay, so here's an overview of how superposition works. We have 2 different pumps here, both of them going out. And if we look at each one by itself and take the equations and the method that we used earlier to measure this drawdown, this H naught minus H. Okay, take the left side. We have one well, and we have this red line here is the drawdown created by that single well. Over to the right side, we have a second well. This purple line, if you can make that out, now that's a drawdown line. for the second well, Q2 over there. So what we do is we just take any horizontal point, any point, move it along, say the x-axis, wherever you want to put it. And here we put B, right in here. Basically what you want to do is draw a vertical line, straight up and down. And you take the drawdown from each side. From the left side we have from here to here, and then from the right side in that spot we have from here to here, and basically all we do is add those two together. So at that point our drawdown is actually going to be right there due to superposition, and you can use this to solve it for really any point at which, well, you're trying to find the drawdown. It's all used the same way. You have all the equations for your R's and for H's, and it works anywhere on this 2D as long as it's a linear system, steady state equations. Sorry, steady state conditions. Okay, moving on to image well theory. So image well theory has, a basis in superposition. That's the first thing, that you need to grasp in the image well theory. And then we're going to make some imaginary wells. They don't exist in real life, but we're going to pretend like they do. And we're going to learn how to locate them, where to put them. And you can have an input well, you can have a providing well, or you can have an output well. We'll talk about how imaginary wells can go either way on that, and then we'll talk about the two different boundaries that basically separate the types of, the ways you can do superposition. Okay, so we have our two types of boundaries here. We have constant head over here, we have impermeable over here. Constant head we'll actually talk about first here. Keeping in mind, point to this slide is this right here is pointing to this water body, and this over here is pointing to this layer of rock. Basically that's what that is, impermeable layer. So here we go with the impermeable boundary first. So impermeable, it doesn't allow flow, that's rocks, mountains, anything that'll completely stop it. Very, very dense stuff, won't allow water through it. So what we're going to do is we're going to place an imaginary well twice the distance as the distance between the impermeable layer right over here and the actual well. So we're going to measure this distance, and that distance is going to equate here. Well, we're going to double that, and that's where we're going to place our imaginary well. So, impermeable, you can have no input flow. So the pump on this is going to be going out. Since you don't have any water coming in, you're pumping out. And so therefore drawdowns, you're going to put those together, and those are generally both going to be, low. It's going low. As you can see here, you have a drawdown and then another drawdown. This next slide might make more sense when I'm saying low drawdown. Okay, and your constant head boundary, constant head increases the water supply in the area. Anything with water, lake, pond, river, anything with water will work. That will cause a constant head. So just like with the impermeable, you're going to measure the distance between the pump and the water, whatever it may be. And that's going to be this distance here. You're going to double that. That's where you're going to put your imaginary well. Okay, since we have water coming in, this is going to be an input well. Water from the water source is coming in the imaginary well. And so when I said low before, in the constant head boundary, you have the pump out, and that creates, a lowered head than the initial, and then the pump in is going to make a higher head than the initial. So basically, if those Q's were the same, this line is going to come somewhere close to the middle due to increased water there, decreased water there. It's not going to be exactly in the middle. A lot of factors involved in that, but you know, it is going to be between the two. And so, just like in the other cases, drawdowns are just summed. You would basically subtract this from this, and that would be your drawdown. Okay, so let's talk about accuracy for a second. The superposition principle it's a theoretical derivation of known laws. Like it involves very, very advanced mathematics, but everything can be written out theoretically. You know, you can actually put pen to paper and write out these equations and how they work together. The image well theory aspect of it it's obviously very accurate. The one possible flaw that I have found in image well theory is based on the fact that when you're drawing your dividing lines, your boundaries, it's a little bitty area kind of right in here that would contain water that it seems does not get added into the equation, and it seems that you know, it makes it easier to make the area if you have a vertical line, but you could use advanced mathematics and calculus to kind of include that little area, but it is, you know, definitely good for making the equations easy to use. Negligible error anyway. Okay, so in conclusion, groundwater hydrology, very important. You know, it allows for determining available water supplies. People got to have water to live, you know, and then if we can find it quicker and easier, you know, determine what's in it, we can get the supply out and everything's good. Also, certain cases, I'm not, you know, promoting polluting the earth or anything, but you take some contaminated water and pump it into the earth. Well, the earth is a natural, basically it's a cleaner. You can put something dirty in there and let it, you know, go through and kind of filter out through the soil, through the other water in there, and it cleans it up for you naturally. Superposition, theoretical derivation from complex mathematics. We've discussed that, you know, that can all be proven mathematically. Image well theory, it's really awesome, you know, it integrates superposition. It allows us to make things, calculate drawdowns where, you know, we wouldn't really be able to calculate it otherwise with the degree of accuracy and the little part that, you know, possibly could be questionable, so little, that's negligible. So future testing, it was initially part of this project. I was going to try to find a study somewhere about maybe, you know, something determining the accuracy in image well theory had been tested before. I was not able to find anything on that. I thought that possibly an idea would be to find a man-made structure that had an observation well in it years ago and now covered with a lake. There's a lake in northern, I guess it'd be considered north central Arkansas, Lake Norfolk, that is a man-made lake, came through, I believe, somewhere between 1940, 1943, 44, somewhere like that. But so it was my intention to try to find readings from an observation well before that was made into a lake, and then after it was made into a lake, to see, you know, there would have to be some assumptions made, but mostly with flow and that kind of thing, but it could be calculated, and it possibly could show any, I guess, error that might exist in image well theory. Maybe the superposition that we're using might be, my guess would be less than 1/100% off, but most likely, again, it'd be so negligible, but that was my intent. I was not able to find any information on it. There were no wells that would read back or that would report that information back in that time. So I was unable to do that. Hopefully somebody in the future might take that idea, maybe prove me wrong, prove me correct. I don't know. I would love to hear about it if it ever comes to be. A list of references for this study, obviously textbook, and I used a lot of stuff from the USGS, and actually a paper that had been given out from a doctor at MIT. So thank you for listening to my presentation on superposition and image well theory. If you have any questions, feel free to contact me via email at temcbrid@email.uark.edu. Thank you and have a great day.